Okay, good morning, everyone. It's nice to see you again. How are you today? Okay. Hopefully, you're feeling encouraged that you're reaching the end of the semester. And then, we get a little break before we start the fall classes again. Just by a show of hands or a comment in the chat window, how many of you are going to be taking fall classes? Okay. All right. I think that's pretty common. So good luck on that fall coursework of yours. I know you're going to do just fine. Okay. I noticed that a few of you were already able to complete the lab exam, and that's fantastic. So for those that haven't done that, please finish that by the end of today. It's not a very long test, and so I think you can complete it and be on to other things. Okay, so please remember to finish the lab exam today. Believe it or not, a week from today is our very last class. Next Thursday, we're not actually going to meet for a lecture because it's your final exam date. Okay, so next Thursday, you take your final exam and it is all over, folks. You're done with your Biology 111. So you can expect that this afternoon, as part of the normal email that I send out, I will include a study guide for your final exam, lecture exam 3. Okay, so expect that you should get that this afternoon. Okay, so between today and Tuesday, we are going to finish up lecture. We're going to finish up our note taking on chapters 12, 13, and 14. Okay, that'll happen by the end of the day on Tuesday, so you're ready to go for your final exam. Do you have any questions at this time about things that might affect you at the end of the semester? Any questions that might be on your mind? Okay. All right, folks. Please let me know. You can always send me an email. I try to check my email once a day so that I can keep up with your comments. Okay. All right. Let's continue. We're going to spend a little bit of time wrapping up some ideas from chapter 12, and then I want to get into chapter 13 this afternoon as well. Okay. Please be advised that because you are taking your lab exam today, and that is the end of the lab experience, that we will not be having a lab time after lecture today, okay? All right, so let's begin. We're going to go back to our shared screen, and we're going to start looking at some more ideas around cardiovascular anatomy. Okay, the chat window is open at this time, so you can make comments and get a hold of me. And also the Word document that you're used to is up. Okay. So at the end of last class, we were talking a little bit about the anatomy of the blood vessels. Okay, and page 215 is your reference page at this moment. Okay, and I had pointed out that arteries are made of 3 layers of tissue. And you see that on page 215 of your book. We noted that the middle layer is made of some elastic material, which allows the artery to be stretchy. And we answered a question. That question was, why is it important that an artery have the ability to stretch? Why is it important that it can be elastic? And that is twofold: to prevent structural damage to the blood vessel and to allow the blood pressure to remain relatively constant. Okay, I believe that's where we finished up last time. Do you have any questions about that content? Okay, all right, so we're going to continue with some ideas here about arteries. Arteries continued. Okay, And so I think, so once again, let's have this idea in our mind that arteries are supposed to stretch. That stretchiness, that elasticity is a beneficial feature of the anatomy of an artery. We want arteries to stretch. Um, However, there are times when, due to age or disease processes, an artery might stretch out, and then it may not return to its normal diameter, its normal size. And when that happens, a certain structure is formed. Do you know what I'm referring to, gang? What is it called when a blood vessel stretches out and does not return to its normal diameter, does not return to its normal shape? What's that called? What is formed? What is formed when a blood vessel overstretches and does not return to its normal size? Okay, thank you, Nick. That's exactly what I'm fishing for, an aneurysm. That's right. Okay. All right. So let's define that here underneath arteries continued. Okay. When a blood vessel, like an artery, overstretches. Okay, you cannot see the screen. Okay. Let's try that again, folks. Pete, you can see the screen. Folks, if you can see the screen, please type yes into the chat window. Okay, let's try this again. I apologize. Thank you for letting me know. Thank you, Marcia and Nick. Okay, let's try that again. Okay, I'm going to do this again. Okay, let's try again. Can you see the screen now? Okay, beautiful, beautiful. All right, okay, yeah. By all means, definitely let me know when we're having a tech issue. Okay, good, good, good. Okay, so let's continue here. When a blood vessel like an artery overstretches without returning to its normal dimensions, we call this an aneurysm. Okay, there's an I in there, and there's a Y in there. Okay, A-N-E-U-R-Y-S-M. Okay, so an aneurysm is a blood vessel. I say it that way. It could be a vein, but it is almost always an artery because the arteries are more susceptible to the formation of aneurysms because the heart is pushing blood directly into an artery when it contracts, right? The heart does not squeeze blood directly into a vein. It only squeezes blood directly into an artery. So aneurysms almost always involve the arteries instead of the veins. Okay. So when an aneurysm forms, that's very serious. The aneurysm is the blood vessel section that has overstretched. An aneurysm does not mean the blood vessel has ruptured. Many people think that. An aneurysm simply means a bulge has formed in the blood vessel. Now, of course, if things are very bad, that aneurysm may in fact rupture. Okay, so I'm going to bring up a small picture on my screen. Okay, here's an example of an abdominal aortic aneurysm. Okay, let me see if I can make this a little bit bigger for you here. Okay, so in other words, you can see what the normal aorta looks like. You can see the normal diameter here where my cursor is on the left side. And on the right image, you can clearly see that where there's an expansion. There's an unnatural enhancement of the diameter. Okay, if that forms, this is the aneurysm. Okay, now aneurysms can form at any part of the body where you have a blood vessel, but obviously some areas of your body are more delicate. For example, if you form an abdominal aneurysm in the aorta, that is extremely serious, right? Because the aorta is the main pumping artery coming off the heart. So if that thing has bulged out, and God forbid it does eventually break and rupture, that can definitely take your life, right? So it really depends where the aneurysm is as to how serious a rupture in the aneurysm would ultimately be. Okay, all right. Folks, do you have any questions about aneurysms? Folks, please raise your hand or type into the chat window if you know anybody who's ever suffered a ruptured aneurysm. Okay, like most things, the older you are, the more you encounter these unpleasant events, right? Let me just share a quick story. My uncle, who's passed away now some years, my uncle was in the Vietnam War, and he was a tank driver, and his tank hit a landmine, and he suffered severe head trauma and lost eyesight out of one of his eyes by hitting that landmine during the Vietnam War. Long story short, after the war, he became a postalman. He delivered mail for a living. And one day he was in a horrible car accident and had a second major head trauma. During his emergency room visit, the doctors discovered an aneurysm in his brain. Okay, so long story short, he went to the Walter Reed Medical Center in Washington, D.C. for evaluation of his aneurysm. And the doctors at the time told him that his aneurysm is pretty serious, but because of its location in the brain, they couldn't guarantee him that they could surgically repair it. In fact, they told him, if you want us to attempt to repair the brain aneurysm, we give you a 50% chance of success. In other words, they thought it was 50% chance that he would get off the operating table and 50% chance he would not get off the operating table. So he chose not to have the surgery and to live with the aneurysm. So he continued to live a normal life for several years after his second car accident. And then one morning he got up, he was in the bathroom doing what we do to get ready for the day. The aneurysm in his brain ruptured. He collapsed and fell into his bathtub, and he passed away just like that. And it was all over. Okay? So, you know, many people have aneurysms and they're not even aware of it. And then they suddenly rupture and they pass away, and everybody's shocked at that. Then you have folks like my uncle, where he was aware of his aneurysm, but there was nothing that could really be done to solve the problem. So he lived with it until it finally did take his life. Okay? So, folks, if you do become aware of an aneurysm, either in yourself or a loved one, definitely seek medical care. That really does need to be addressed. Okay. Do you have any thoughts or questions? Pete, what are the symptoms of it? Well, Pete, it depends where the aneurysm is. Sometimes there are no symptoms whatsoever. In other words, in the case of my uncle, he was not aware of the aneurysm. The only reason they discovered it was because of treating him during his second car accident. That's how they discovered it. But in some cases, there are simply no warning signs that you have an aneurysm. Okay, depending on its location, you might have some weird sensations in the body, like you might be getting unusual headaches or things like this. You might be getting abdominal pain if you have an abdominal aneurysm. You might have muscle discomfort in the leg if you have an aneurysm in the leg. It really varies, and it's really kind of hit or miss whether you're going to have a symptom that you're aware of to go get checked out. And that's really the danger here. Okay. Other questions? Okay. In many cases, you'll hear stories of how someone discovered an aneurysm because they went in for medical care for another reason. And during that treatment for a different problem, the aneurysm is in fact discovered. Okay, let's continue here. I'm going to share my screen again. Okay. All right, so the chat window is back up. If you have any problems, please let me know. Okay. The bulge in the blood vessel is the aneurysm. Okay. When an aneurysm ruptures, depending on its location, it can be life-threatening. Okay. All right, folks. The next topic that I want to cover here under the continued discussion of arteries is, in fact, that of your pulse. Okay. All right. Your pulse, gang, is a vibration in the artery that's created during the continual opening and closing, the continual expansion and contraction of different sections of the artery at slightly different moments of time by the passage of blood through the blood vessel. Let's type this out into your notes, and then we'll go to a PowerPoint drawing to try to sketch this out a little bit. A pulse is the vibration. It is the vibration. Okay, I'm trying to emphasize an idea, which is why I'm keeping the words "is the vibration" in capital letters. The pulse is the vibration in an artery created by the continual expansion and collapsing of different sections of the artery at different moments of time. Okay, once again, the pulse is the vibration in an artery created by the continual expansion and collapsing of different sections of the artery at different moments of time. Okay, so I'm going to go to a PowerPoint drawing here. All right. Okay. All right, so we have PowerPoint up at this time. And let's just sketch this out a little bit here, okay? What we really mean by the pulse. Okay, so let's see here. Okay, so if we have a section of artery, okay, here's an artery, okay, and I'm not much of an artist, but okay, so let's say this is a section of artery. Okay, and let's say that we have a blood front. A blood front is the front of a volume of blood that is moving into the artery because the heart just contracted and is pushing the blood forward through the cardiovascular system. So here we have blood. Okay, here's the blood front. Okay, think of the blood front like a wave. If you think about a wave at the seashore, right? Hopefully some of you have gotten down to the seashore this summer, or you will later on. Okay, and you see the waves of water coming up onto the beach, right? You can kind of see the front of the wave as it approaches your position on the beach. So it's kind of like a wave. Okay. Thank you, Matt. Okay, so you can imagine, gang, that as this blood moves into the anatomy of the artery, that wherever that blood is at that moment in time, that section of the artery, which I will simply change color on here to try to illustrate something, that section of the artery, wherever the blood is at that moment in time, that section of artery is going to expand outward. Okay, that's part of the elasticity and the stretchiness of the structure of the artery, because the heart is squeezing an additional volume of blood into the confined space of an artery. So as we talked about last time, the stretchiness of the wall of the artery will allow the diameter here to increase so that we can accommodate this increase in blood without a dramatic increase in blood pressure. Okay, so that will continue wherever the blood front is, right? In the next moment of time, the blood's now going to be down here. And that means wherever the blood is at that moment in time, that localized section of the artery is in fact going to expand out. It's going to stretch out to accommodate that extra blood, right? Now think about it. We've graphically shown two areas of the artery that is stretched out. So the first one is time point 0. Time point 0, and the next one is time point 1. So you can appreciate that if the blood is at time point 1, that corresponding section of artery expands outward. But since the blood has moved past the section of time point 0, that section of tissue goes back to its normal diameter. It collapses back to its normal size. So after the blood has moved past that location, these little green humps will collapse back to their normal diameter. Okay. Okay. Folks, am I making a little bit of sense here? I hope I'm making a little bit of sense. Does it make sense that as the blood moves into the artery, wherever the blood is, that section of the artery expands? Then as the blood moves past that section, the next section of artery expands while the previous section collapses back to its normal resting diameter. Does this make sense to you? Please let me know in the chat window if you're understanding what I'm saying. Okay, thank you. Okay, so this continues obviously through the entire length of the artery as the blood moves through it. So we have different sections of the artery expanding and collapsing at different moments of time. And as different sections stretch out and different sections come together, that literally creates a vibration in the blood vessel wall. And that vibration in the blood vessel wall is what you and I and doctors call the pulse. Okay. The constant stretching and collapse creates a vibration in the arterial wall. That vibration is the pulse. Okay. All right. Questions at this time? All right. Not seeing anything. So let me just kind of wrap this idea of the pulse up with just a quick little story here. Okay. Folks, do you remember the former Vice President of the United States by the name of Dick Cheney? Okay. You may know if you followed any information about him that he has had heart trouble most of his adult life. And in fact, today I believe he is a heart transplant recipient. okay? But all politics aside, and whether you liked him or didn't like him, he struggled with heart problems all his life. And there was a moment in time where, before he got his heart transplant, doctors surgically put in a mechanical device called a ventricular assist pump. Okay, a ventricular assist pump. Okay, and so I'm going to show you what this device kind of looks like. Okay, hold on a second while I share my screen again. Okay, so we're back up to PowerPoint, and now, okay. So if you cannot see this picture of the ventricular assist device, please turn on your microphone and let me know if you cannot see it. Okay. So a ventricular assist device is exactly what this image is showing you. Here down here we have this mechanical pump that's connected to the left ventricle of the heart, which is the main pumping chamber for the systemic circuit of blood flow. And you see that it takes the blood and then accelerates it through the machinery, through the rotary machinery of the pump, and pushes it back up into the aorta, which is the main artery of the body that will then disseminate the blood through the rest of the body. Okay, so there was a moment in time when Dick Cheney's heart was so weak that they needed to give him this mechanical assist device. Okay, so now here's an interesting little quirky kind of Ripley's Believe It or Not. For many folks that get a ventricular assist device, basically their pulse disappears. So a person with a ventricular assist device, they have their pulse go away. Can you explain to me why it would go away? What do you think, gang? Why would Dick Cheney's pulse disappear when he had a ventricular assist device put in? Okay, so yes, Nick has hit it for us here, and and thank you all for cooperating here and for contributing. Okay, think about it. With the normal beating of your heart, the heart contracts, pushes blood, and then for a brief moment in time, the heart relaxes and it simply rests and doesn't do anything. I mean, it doesn't move any blood. So you contract, push blood, rest. Contract, push blood, rest. That intermediate pulsing of the heart causes pulsing of blood through the anatomy of the artery, so that different sections open and close along the length of the blood vessel, because blood is being ejected into the blood vessel intermittently. Nick has the right idea. With a ventricular assist device, there's a pump with a rotor in there that's spinning constantly and constantly pushing blood through the artery. So in other words, when you have a ventricular assist device, the anatomy of the artery opens up and it never collapses. It opens up and it stays open. There's no time for rest, because the mechanical nature of the machine pushes blood constantly rather than intermittently through the anatomy of the blood vessel. Do you see how that would work? Okay, with the anatomy of a normal blood vessel, you get this kind of behavior. Open, close, open, close, open, close, open, close, corresponding with the heart contraction and relaxation. But with the machine, you get open and it stays open because the blood's constantly moving through that artery. Folks, do you see any irony in having a politician who does not have a pulse? Okay, you will in 20 years. Okay, all right. Folks, any questions right now? Okay, let's continue. And we're back here to the Microsoft document and chat windows open. Okay. All right, folks. Let me just move on here. We're going to talk about capillaries next, and I'm just going to summarize things that you already know, okay, because we're talking about blood vessel anatomy, and probably the most significant things I could tell you at this moment was the artery information, right? So blood vessel anatomy continued. All right, let's go with capillaries at this point. The capillaries are the tiniest blood vessels of the body. As you know, they are the marketplace of exchange. For pushing oxygen into the tissue, removing carbon dioxide, that sort of thing. Okay. The blood vessels are so small that individual red blood cells have to pass through single file. Okay. All right, so that's just to keep your notes consistent and correct. Let's talk about the veins. Okay. As you recall, the veins are the blood vessels that return blood to the heart. Okay. If you were to look at the anatomy of a typical vein and compare it to the anatomy of a typical artery, as you can do on page 215, you would notice a few things. First off, if you look at the thickness of the wall of the vein, it is thinner than the thickness of the wall of an artery. Okay. On average, the wall of a vein is thinner than the wall of an artery. Why is that true? Why would a vein have a thinner wall? Why is that? Why would a vein have a thinner wall than an artery? Keep the blood flowing? Well, we definitely want to achieve that. But yeah, Matt has hit on something here, right? There's less pressure, right? Remember that the heart never ejects blood into a vein. Okay, there are no veins receiving blood from heart muscle contraction. So therefore, the amount of pressure inside that blood vessel is less, so the wall of the vein does not have to be as structurally robust to withstand the high pressures that an artery does. Okay? All right. So veins experience less blood volume and pressure than a comparable artery. Okay. Couple other things here. Just some talking points that you should be aware of as you do your own study time. Okay, on average, the vein, the lumen, the open hollow space of a vein, on average is going to be a great deal larger than that of an artery. If you look at the picture on the bottom right corner of page 215, notice you have a vein there. Look how big the open hollow space is, okay, of the vein compared to the artery. It's a lot bigger, okay? Notice that veins have a large lumen, which decreases friction of blood, well, it decreases the resistance to blood flow. Allowing blood to move easily through the veins. In addition to that, your veins have these structures which are valves, which you can see on page 218, figure 12.6. These one-way valves help ensure that blood is always moving in the correct direction towards the heart rather than away from the heart, right? The blood needs to continue its journey in the veins and get back to the heart. So the presence of the one-way valves helps ensure that. Veins contain one-way valves to ensure blood moves in the proper direction. Okay. Sometimes folks, you might be out, particularly in the summertime when people are wearing, shorts so you can see their legs. You might see folks that have discolored veins or areas of their legs where you find bulges, and you may know what these are. These are varicose veins, right? Okay. So varicose veins occur when valves malfunction and become leaky, allowing blood to collect or pool behind the valve. Okay, so if you've ever seen, someone that has some unpleasant looking veins in their legs or arms, most usually it's because they are varicose veins. Okay, folks, any questions so far? Okay, folks, we're going to change topics now, and we're going to move into heart anatomy. Okay, heart anatomy. Please, if you have your book in front of you, please turn to page 220. Okay. And so, excuse me, we're not going to go into exhaustive detail. If you do end up taking our anatomy and physiology course at HAC, you will need to know heart anatomy very deeply, and you will have to understand and know and be able to explain the flow of blood through the anatomy of the heart. Okay, that's appropriate for somebody going into a medical field. But for folks here at 111, we're just going to give you a general familiarity with some things that you may have heard about before. Okay, so let's talk about heart anatomy. First off, we have the myocardium. The myocardium is the heart muscle. It's the tissue of the heart that makes up most of the mass of the heart. This is the tissue of the heart that makes up most of the heart mass. This is made of cardiac muscle fiber. Okay? And so please try to put your eye on these structures on page 220 as I list them out as I list them into your notes, so you know what I'm talking about. Okay. So myocardium is the cardiac muscle fiber of the heart. Next, we have the endocardium. Okay. The endocardium is the inner lining of the heart, the inner lining of the chambers of the heart, which is made of a specialized epithelial cell, specialized epithelium, which we call endocardium. Okay, so this is the thin inner layer of tissue that lines the cavities of the heart. And if you've ever heard about a heart patient having endocarditis, that's telling you that they have inflammation of the endocardium, right? That's what that's referring to. Okay, it is made of specialized epithelium. Okay, next is the pericardium. Okay, and we're going to start here and point out something. Technically speaking, folks, the pericardium is not part of the heart. It's not part of the heart, okay? That being said, while the pericardium is technically not part of the heart, we often talk about it because, you know, when you look at the anatomy of the heart, the pericardium is sitting right on the outside surface of the heart. So there it is. Okay, take a look on page 220. It's this fibrous sac that the heart actually sits inside. Okay, pericardium is a fibrous sac that the heart sits inside. The pericardium helps the heart stay in its proper location in the middle of your thoracic cavity. The middle of your thoracic cavity between your lungs has a special name in anatomy. It's called the mediastinum. Okay, so the pericardium helps the heart stay in the mediastinum. Okay. The pericardium is a fibrous sac that the heart sits inside. The purpose of the pericardium is to hold the heart in its correct location inside the thoracic cavity. Okay. So, you know, if, you know, all kinds of good things happen in life, but when it comes to medical issues, usually if you're talking about a medical issue, it's because something bad has happened, right? So, you know, if someone's unlucky enough to bruise their heart by being in a car accident or something like that, the heart might bleed, right? And if the heart literally bleeds, then the blood leaving the heart actually goes into the pericardial sac and it gets trapped there. And unfortunately, if it gets trapped there, the heart literally begins to drown in its own blood, and that can also be life-threatening, right? So you can have all kinds of nasty things, right? You can have endocarditis, which is an inflammation of the endocardium. You can have pericarditis, which is an inflammation which might be associated with the presence of a bacterium or other microorganism that's made its home in the pericardial sac. You can have bleeding of the heart, which traps the blood in the pericardial sac so that the heart literally drowns in that blood. All kinds of nasty things can unfortunately happen at times. Okay, let's continue here. Number 4, the atria being plural, right, and atrium being singular. Okay, the atria are the upper chambers of the heart, and as you probably know, they receive blood back from the circulation. Okay, so blood that's returning to the heart is going to be delivered into the heart in the right and left atria. Upper chambers of the heart that receive blood into the heart. Okay. The lower chambers of the heart are your ventricles. Okay. And the lower chambers of the heart, they will receive the blood from the atria. And once they receive it, they will eject blood into an attached artery. Okay, if it's the left ventricle, you're going to eject blood into the aorta, and that'll move blood through the systemic circulation. Okay, so the ventricles are connected to an artery, and they push blood out of the heart. Okay, these ventricles are very muscular. Okay. All right. So now I'm going to keep rolling here. Quinn, you asked a question. What is the pericardium a part of? Okay, so the pericardium is not part of the heart. The pericardium is part of a network of connective tissue inside your body whose entire function it is simply to hold your internal organs into the proper location. Okay, so you have all these membranes inside your body cavities, inside your abdominal cavity, inside your chest cavity, and their job is to wrap around the internal organs and kind of hold them in place. These membranes are literally connected to the inner lining, in the case of your chest cavity, the inner lining of your chest cavity wall, right? It's like taking a soccer, it's like taking, I don't know, it's like taking an equipment bag for a bunch of soccer balls and stitching that equipment bag to the inner wall of your garage so that the balls stay in location. Okay, that's what all these membranes are doing inside your body cavities. Other questions? Okay, please ask away. I'll try to keep up with them. Okay. Next are your valves, gang. Valves. Okay, so we need to talk about that. There's two kinds of valves. There are the atrioventricular valves, and there are the semilunar valves. Okay, so as you look on page 220, okay, notice that the valves are these kind of whitish gray flaps of tissue, and you see them there, right? You see the right atrioventricular valve there and the pulmonary semilunar valve as examples. You see more valves and more realistic pictures of them on page 221, figure 12.8. Okay, so these are your heart valves. Okay, the whole purpose of your valves is to prevent backflow. Prevent the improper backflow of blood. Okay, so atrioventricular valves are valves that are located in between each atrium and its attached ventricle. Okay, and their job, as we've highlighted here, the job, for example, the job of the right atrioventricular valve on page 220, its job is to prevent backflow of blood from the right ventricle into the right atrium. Blood should never be moving from the ventricle to the atrium. We want it to move from the atrium to the ventricle, so it is the function of that valve to prevent backflow. Okay. The semilunar valves are located between each ventricle and their connecting artery. Okay, so as an example, the pulmonary semilunar valve there, right? You see the pulmonary semilunar valve on page 220 there. Its job is to ensure that blood does not backflow from the left pulmonary arteries into the right ventricle. We don't want that to happen, okay? That would be improper. So again, the function of the valve is to prevent that. Okay, so it's here where we're going to get to talk about a silly little thing. Take a look, folks. When you look at page 220, let me ask you, okay, I'm going to ask this through the chat window. What is the name of the heart structure that connects the valve, that connects the right atrioventricular valve to the heart wall? What is the name of the heart structure that connects the right atrioventricular valve to the heart wall? Okay, thank you for trying, Pete. It's not pulmonary semivascular. When you look at the anatomy on page 220, okay, look at the valve, and there is something connecting it to the heart wall. Let me give you a hint. The structure I'm fishing for kind of looks like a thread. Okay, Alyssa, thank you. That's what I'm fishing for. The chordae tendineae. Folks, the chordae tendineae are straps of connective tissue that literally hold the flaps of the valve in place against the internal anatomy of the heart wall, okay? What I'm trying to tell you, folks, is the chordae tendineae that you look at on page 220, those are your heart strings, okay? So every Valentine's Day when someone tugs on your heartstrings and your heart goes pitter-patter, they are anatomically tugging on your chordae tendineae, okay? Notice the chordae tendineae, okay? These are your heartstrings, okay? The purpose of these heartstrings is to prevent the valve flaps from going, the purpose of the heartstrings is to prevent the heart valve flaps from inverting and kind of turning inside out. Imagine for a moment what it looks like to have an umbrella out in a windstorm. It doesn't take very long for the umbrella to turn inside out, does it? And the umbrella is often ruined, okay? So you don't want your heart valve flaps to invert like that. And so the chordae tendineae helps stabilize the flaps so that they don't invert into the atria. The purpose of the chordae tendineae is to prevent heart valve flap. The technical term is eversion, okay? Is to prevent heart valve flap eversion, meaning we're preventing the valve from turning inside out. Okay. Questions so far, gang, about heart anatomy? Actually, we're almost finished with the portion of the anatomy that I'm going to talk about. Do you have any questions at this time? Okay. Let me do two more things on this topic with you, and then we're going to start wrapping things up for chapter 13. First off, it might be of interest to you to know where your heart's pacemaker actually is, because you may not know anybody, but certainly people around the world have pacemakers in them. Pete, are animal and human hearts different? Yes, they are different, and obviously it depends what animal you're talking about. But even though they are different, there is a remarkable amount of similarity. In fact, that's one of the reasons that hearts from pigs have often been used for replacement parts like valve flaps and things like this. So yes, they are different, but at least for some animals that are evolutionarily related to us and fairly close to us, like a pig, they're not so different. Okay. So let me just highlight the pacemaker of the heart you find on page 224. Okay, and actually there's more than one pacemaker. The primary pacemaker of your heart is the sinoatrial node that you see in figure 1212. Okay, now when we talk about a pacemaker, we're talking about a cluster of cells, a group of cells that have the ability to electrically excite muscle contraction in the heart. Okay, pacemakers are groups of cells that can electrically excite the muscle fiber of the heart. Okay. The sinoatrial node you see there is in the upper part of the right atrium. Okay. It has the ability to electrically excite and generate and establish the rhythm of the heart. Okay. When a person needs a pacemaker put into his or her chest, it is almost always the sinoatrial node that needs replaced. Okay, because of disease or age that has damaged that group of cells, they can't do their job anymore. Okay. The sinoatrial node is the primary pacemaker. And the primary pacemaker, this is one that is most normally replaced by an electronic device that serves the same role. Okay. Okay, and is supplemented with an electronic pacemaker. All right, so the sinoatrial node is the main pacemaker of the heart. In addition to that, there is a backup pacemaker called the AV node, the atrioventricular node. Okay, the atrioventricular node is literally located between the atria and ventricle there that you see. Okay, and it is in fact a backup pacemaker. Okay, Mother Nature designed your heart with redundancy, folks. In other words, many backup plans. The atrioventricular node, if the sinoatrial node fails, the atrioventricular node can keep you alive. Okay, and this might be extreme, but Mother Nature did this. There is a third backup pacemaker group of cells called your book on page 224 says the bundle of conducting muscle cells. your book is kind of removing some of the technical detail. That group of cells is called the bundle of His, H-I-S. Okay, the bundle of His. This is a backup to the atrioventricular node. Okay, so you have, folks, a marvelously engineered organ called the heart, which offers triple redundancy to keep your heart beating and the blood flowing through your body, which is really amazing if you think about it. Okay, folks, do you have any questions at this time? You know, we could go on and on for the rest of today's class because there's plenty here to do. What I want to do is finish up chapter 12 by showing you a video about the cardiac cycle, which is to say the series of events from the electrical excitation of the muscle fiber of the heart to the mechanical contraction of the heart in such a way that you move blood through the heart and into the body. That's the cardiac cycle. Okay, I could spend the rest of my time describing it to you, and I think a cartoon will simply do a better job and give you a way to visualize this. Okay, so let's watch a video of the cardiac cycle. Okay, so bear with me one moment. Okay. So here's about a 4-minute video called How Does Our Heart Work? The Cardiac Cycle. Please listen carefully. The narrator of the video does use has a bit of an accent, so it's a little bit hard at times to understand, but stay focused because the video shows you some good stuff. Okay, so here we go. And here we go.
As we unravel the mystery of the rhythmic beating of the heart, we come to realize that heart performs this function with flawless consistency. The heart is an organ that beats throughout the lifetime of a person. Are you aware that in an average lifespan of 70 years, it beats about 2.5 billion times? The heart beats rhythmically due to the electrical impulses which cause synchronized contraction of the heart muscles. These impulses cause the contractions of the atrium and the ventricles, which allow the heart to pump blood. But have you ever wondered what controls the heartbeat? Cardiac pacemaker. The heartbeat is generated and controlled by a pacemaker present in the heart. It also possesses specialized excitatory conducting system which ensures the rhythmic beating of all the cardiac muscles. The walls of the atria form the atrial syncytium, and the two ventricular walls constitute the ventricular syncytium. The pacemaker is located in the wall of the right atrium. It is also known as sinoatrial node or SA node. The SA node generates an impulse which spreads across the walls of the atria through the specialized conducting system, causing both atria to contract in unison. During atrial contraction, this electrical impulse reaches the atrioventricular node or AV node. Here, the impulse is delayed for about 0.1 second, after which it moves along the bundle of His, bifurcates into bundle branches before spreading along the Purkinje fibers. The impulse reaches the lateral ventricular walls and causes its contraction. Thus, the impulse generated at the SA node causes atrial contraction and flow of blood into ventricles, and then the ventricles contract, pumping the blood out of the heart. It is the impulse generated by the SA node that causes the heart's chamber and valves to work in tandem. Thus, we conclude that it is the SA node as the cardiac pacemaker which sets the rhythmicity of the heartbeat. Summary. We can now observe the impulse conduction and heartbeat in synchronization with the blood flow. The cardiac cycle begins with the SA node generating an impulse which spreads to the two atrial walls and also reaches the AV node. The two atria which form the atrial syncytium contract. The AV node delays the transmission of the impulse by 0.1 second, which allows the atria to empty completely before the ventricles begin to contract. Then the impulse moves along the bundle of His and finally through the Purkinje fibers to spread all over the ventricular walls. Finally, the ventricular syncytium contracts, thus pumping the blood out through the aorta and pulmonary artery. This is the end of one cardiac cycle.
Okay, folks. All right. Are there any aspects of cardiovascular function or anatomy that you would like to ask about before we start the next chapter? I mean, as you saw from the video, which I think is a pretty nice video, I don't think there's any video game music in your heart, but the video did a nice job of showing you how the blood moves in a rhythm that is created by the electrical tissue of the heart. Okay, your body does this 2.5 billion times by the time you're 70 years old. Okay, and it doesn't stop. It cannot ever stop. Anything you'd like to ask about? Okay. You know, we haven't talked about diet and nutrition in this course, which is a little unfortunate, but there's only so much we can do in an 8-week class. Suffice it to say, you do want to pay attention to your diet, folks. Don't eat a lot of fatty foods because you really do not want the development of atherosclerotic plaque in your blood vessels, because that's what's going to lead to a heart attack and potentially stroke, okay? So it really does matter what you ingest. Your food can be your medicine or it can be your poison. So you want to develop, as best you can, good eating habits, eating nutritious food and not overeating. It's always easier said than done. I do appreciate that, okay? But do your best, because that plaque starts to accumulate in your body, you know, in your 20s, 30s, 40s. And by the time you're 40, you're about a 5-time greater risk of having a heart attack than when you were in your 20s. Okay? Questions, gang? The other thing I want to encourage you to do is, if you don't, and you're willing to do it, is try to be a regular blood donor, right? We need blood donations all the time. And I say that because not only when you donate blood might you help another human being, but believe it or not, donating blood also improves your health. I think I mentioned last time that at least in the US, it's very, very common for Americans to have elevated iron levels in their bloodstream. That's a bad thing. You don't want elevated iron levels in your bloodstream. By donating blood, you reduce the iron levels, and that helps reduce inflammation in your blood system. Okay, so it's not just beneficial to someone else when you donate blood, it also helps you too. Okay? All right, folks, any questions? Okay, let's keep rolling. We have an hour. We're going to get into chapter 13. Here we go. Okay, chapter 13 are body defense mechanisms. If I'm being frank with you, this is one of my favorite chapters because I'm very interested in the immune system. Okay, so hopefully you'll be interested too. It's a really cool thing. Body defense mechanisms. Okay. This begins on page 239, 240 of your textbook. So I encourage you to have that open and available to yourself. Also, the chat window is up on my screen. So if you need to get a hold of me, please go ahead. Okay. So, you know, we will be lucky. We will be lucky if we even talk about the immune system today. And why I say that is because body defense is not the same thing as the immune system. Body defense is a bigger, broader topic. The immune system is only part of it. Okay? So let me just define two terms here because we need to be on the same page when we're having a conversation about body defense. And the first is pathogen. Okay? Folks, a pathogen is any disease-causing microorganism. Okay, so right now the coronavirus, which is causing a great deal of heartache around the world, is a pathogen. That virus is infecting us, it's creating disease, and for some folks, it's taking their life. Okay, so pathogens, any disease-causing microorganism. An antigen. An antigen is a molecule that stimulates the immune system. Okay. So I have a question for you. Which is larger, antigen or pathogen? Which is larger, antigen or pathogen? Okay, good, good. I just want to be sure we're on the correct path here. Absolutely, right? A microorganism is going to be a virus or a bacterial cell, which is made of potentially billions and billions and billions of molecules. Okay, very good. Pathogen is drastically larger. Okay. Okay, so in your book outlines body defense by introducing this idea of 3 lines of defense. You see that as the first talking point in the upper left corner of page 240. So let's list the 3 lines of defense out, and then we will start picking them apart, okay? Body defense as 3 lines of defense. Okay, so we have the first line of defense. And the first line of defense is made of 2 basic ideas, things that are referred to as physical barriers and things that are chemical barriers. Okay, so for physical barriers, I don't think I need to define it for you. I'll simply give you a few examples, and I think it will become obvious what we're talking about, right? Probably the easiest thing we could talk about would be your skin. Surely you appreciate that your skin defines the transition from the internal environment of your body to what's outside your body. So your skin is a physical barrier. It helps prevent microorganisms that would want to get into your body. Okay, skin's a physical barrier. Also, mucous membranes, right? You have mucous membranes throughout your body, but think about the mucous membranes that you have in your nose and your respiratory tract there, right? I mean, you breathe in air, and some of the dirt and particulate matter, maybe mold spores, things like that, maybe dander from the animals that you live with, some of that junk that's in the air that you're inhaling, it will be caught in the mucous membranes of the respiratory tract. And then one of two things is going to happen. Either you're going to sneeze that material out of your body, hopefully into a tissue, or you might actually swallow that material down into your stomach, where the hydrochloric acid in your stomach will destroy what's ever there. Okay? So mucous membranes would represent another kind of physical barrier. Let's see, what else could we say? Actually, the motion of your body fluids is often seen as a physical barrier to infection. So as an example here, motion of your bloodstream. Okay, think about it. Many times for a microorganism like a bacterium to cause you harm, they have to be able to physically attach and stick to an internal body surface. If they can't attach, quite often they cannot stick around long enough to cause any harm to that location. Excuse me a moment. Okay, let's continue. So if you have a microorganism, a bacteria in your bloodstream, if it can attach to the inside of an artery, it's much more likely to create inflammation, which might then lead to the development of atherosclerotic plaque. And in fact, scientists are starting to think that at least some percentage of plaque buildup in our arteries are initially seeded by microorganisms that are able to attach to the inside of a blood vessel wall. Okay, which is kind of a weird idea to think that plaque is due to microorganisms floating around in our bloodstream. Okay, but there is evidence to suggest that is happening. At any rate, the actual motion of your blood helps prevent the microorganism from attaching to the inside surface of the blood vessel wall, and that is physically protective for you. Think about what it's like to, I don't know if any of you, if any of you have ever gone whitewater rafting, please indicate so in the chat window. Have any of you gone whitewater rafting? Or even just tubing of some kind? Okay. Is Pakasha the only one? All right. All right. So, okay. All right, good. There we go. There we go. If you haven't had a chance to go rafting or tubing, I would encourage you to do it. You don't have to be crazy about it. There's some gentle ones that can be very enjoyable. But if you have any experience with this, you know there's different categories of rapids. Class 5 rapids are extremely violent and dangerous. And you would be insane to do a Class 5 rapid unless you have a great deal of experience handling the water. Okay, it's not for a beginner. Well, think about it. How difficult would it be for you as a human being to get dropped into the middle of a Class 5 rapid and swim out without drowning? That's the kind of scenario it is for a bacterium floating in your bloodstream that's being accelerated to a tremendous speed by the contraction of your heart muscle. Okay, when you drop a bacterium into the bloodstream, that bacterium is kind of like you trying to swim and float around a class 5 rapid. Okay, so in that context, it's actually good that the motion of your blood to a large degree prevents bacteria from sticking to the blood vessel walls. Okay, same thing's going to be true of bacteria that might like to set up shop in your urethra, right? The motion of the urine through the urethra is also going to be physically protective for you. The same thing's going to be true for the motion of tears across the surface of your eyeball. That helps prevent microbes from sticking to the surface of your eyeball. So the motion of these body fluids is a physical barrier to prevent attachment and prevent infection. Gang, are you okay with physical barriers? Does it make sense what I'm trying to tell you? Okay. All right. So those are physical barriers: skin, mucous membranes, motion of your bloodstream and other body fluids. Next, we have the chemical barriers. And we'll give you some examples here. Okay. All right. Your skin. Okay, folks, so your skin is obviously a physical barrier. You can appreciate that. We've listed it out. Your skin's a physical barrier. But it's also true that on the surface of your skin, you have a very light film of a skin oil, right? Go ahead and rub your thumb against your first finger. Don't they glide across each other without causing pain, without sticking, without tearing each other, without tearing the flesh of each finger, okay? So you have a thin film of oil on the surface of your skin, and that oil has chemical properties, so that oil is a chemical barrier. Specifically, the oil on the surface of your skin. And what makes this skin oil protective for you is that it has a very mild acidic pH. Skin oil is mildly acidic, and acidic environments are largely inhibitory to many species of bacteria that would like to live on the surface of your skin. It's antibacterial for many, but unfortunately not all, species of bacteria that would like to live on your skin. Okay. All right, so your skin oil is acidic and it's largely antibacterial and it's protective for us. Okay. What is the exception to the rule for bacteria that live on our skin? What I'm fishing for is something that you might be aware from experience in the medical setting or in nursing homes. There's a type of bacterium that does like to live on your skin, and it causes a great deal of harm. What's the name of this bacteria? What bacterium does live on your skin because it enjoys acidic environments? Do you know? Okay, well, I'm not sure what you mean by hairs, Pete. The hairs themselves are not bacteria. Folks, what cellulitis is a cell condition where you have inflammation of the cell that might lead to death of the cell And cellulitis could be triggered by this bacterium, but cellulitis is not the bacterium. C. difficile. C. difficile is more of an intestinal parasite. Yes, I do mean.
Are you referring to staph infections?
Yes, I am. Do you know the specific version of do you know the full name of a staph infection?
No, I'm not 100% sure.
Okay, all right, but thank you. You do, you're on target. Folks, I'm talking about MRSA, M-R-S-A, which is an abbreviation. Does anybody know what each of those letters stands for? Okay, well, come back and take our microbiology class. We'll teach you all kinds of gross things. Okay, MRSA is short for methicillin resistant Staphylococcus aureus. Methicillin resistant Staphylococcus aureus. This is a specific subtype of Staphylococcus aureus bacteria that enjoy living on the surface of your skin because they actually like the acidity of your skin oil. And unfortunately for us and problems for the medical community is that this category of bacterium is resistant to drugs, resistant to antibiotics that are based on a chemical called methicillin. Okay, so it is a big problem for us. Okay, all right, so skin is the skin, but specifically the oil on the surface of the skin is really the chemical barrier. Some other things, saliva. Okay, saliva has chemicals in it that are also antibacterial in nature, just as an example. There is a molecule in your saliva called lysozyme, not to be confused with lysosome. This is lysozyme. Okay. Lysozyme is an enzyme that degrades the peptidoglycan layer, of bacterial cell walls. Okay, so saliva actually has enzymes in it that reduce the population of bacteria that are in your mouth. And let's see here. Well, okay. I guess I'll leave it at that for right now. Folks, do you have any questions about physical and chemical barriers? Physical barriers are preventing the microbes from getting into our body or preventing them from attaching to our body structures. Chemical barriers also prevent them from staying place, or the chemical barriers actually destroy the microorganism. Any questions? Okay, let's keep rolling here. Number 2, the second line of defense. Second line of defense. The second line of defense is made of a group of different things, that are somewhat related but somewhat different from each other. Okay, the second line of defense is sort of a category where we throw everything in it but the kitchen sink. Okay, so let me list some ideas out here and then we'll talk about them. The second line of defense is made of your defensive cells, defensive proteins, a responsive tissue known as inflammation, Okay, we've talked about inflammation. We're going to start talking about what it really is in just a moment. And fever. Fever is considered part of your body defense, and it's organized into the second line of defense. All right, so let's talk about defensive cells. Okay. Now, for defensive cells, I don't have to go too far because you already have some introduction to this from chapter 11 when we talked about the white blood cells, all right, which is just a lecture or two ago, okay? But when we talk about defensive cells, we could talk about phagocytes. Okay, a phagocyte is any cell that can eat another cell. And we introduced you to two categories of phagocytes in this course. We introduced you to neutrophils. And I believe we also introduced you to macrophages. Okay, so neutrophils and macrophages are just two different kinds of cells that are both phagocytic. They both have the ability to eat things. And so it's kind of neat on page 241 of your book. You have figure 13.3 there. That's an example of a macrophage getting ready to ingest or phagocytose a bacterium. You can see that the macrophage, which is really that big blob of material at the top of the picture, is extending this cytoplasmic bridge down below to that tiny little cell down there that kind of looks like a sausage link, which is the bacterium. Okay, so you can see that a macrophage is huge compared to the size of a bacterium. And usually we don't like bullies in society, but in the case of one of your defense cells protecting you from disease and illness, I'd be okay with having it be a bully, right? The macrophage is gigantic compared to that bacterium. Okay. Let's see, other categories of defense cells that we have talked about here would include eosinophils, which we mentioned protect you against parasitic worms. There's also a category of white blood cell we did not talk to you about, but it's introduced in this chapter called natural killer cells. Natural killer cells. Okay. You can see some natural killer cells on page 242 of your book, figure 13.4. They are artificially colored orange. They're artificially colored orange in your textbook, okay? Natural killer cells are cells that attack abnormal human cells. They attack abnormal human cells. And so, you know, what do we mean by an abnormal cell? Well, typically an abnormal cell, you know, there has to be something that makes a cell stand out as being abnormal. Well, usually those kinds of cells have molecules on their surface that normal healthy cells don't have. And they have these molecules because the cell has either been infected with a virus, or the cell is experiencing abnormal gene expression because it's kind of cancerous, okay? So natural killer cells will attack virally infected cells and or cancer cells, okay? And so you see the natural killer cells on page 242, they're orange, and at least in the coloring of that picture, the cancer cell, the leukemia cell, is being artificially colored red, okay? Any questions at this time? Folks, let's talk about the natural killer cells. Okay, so natural killer cells will attack cancer cells or cells that are kind of on the verge of becoming cancers, sort of precancerous cells. You think about it for a moment. Isn't it pretty much true? Let's see here. How many people are on planet Earth at this time? What's the world population? Anybody quickly Google that for us? Okay, Quinn, 7 billion I can work with. Latest figure I saw had it around 7.6 billion. So we're closer, I think, to 8 billion people on the planet than we are to 7 billion. But the point of it is there's a lot of people. Doesn't it make sense that with 7 or 8 billion people on the planet, we are guaranteed, we are absolutely guaranteed that at some moment, that at any given moment of any given day, there's at least a few people of the 7 billion that are pissed off about something badly enough that they're going to do something that's very antisocial. Is that a fair statement? That with 7, 8 billion people on the planet, every day there's going to be at least a few people that are upset enough about something to do something antisocial. Would you agree with that? Okay. I hope that's not a stretch for you. I mean, just turn on the news, right? You can see what's happening in Portland and so forth. But at any rate, if 8 billion people have a couple people every day at least that are upset and do bad things, isn't it that much more believable that your entire human body, which is not made of 8 billion people or 8 billion cells, but instead 80 trillion cells, 80 trillion cells, doesn't make sense that in that body of 80 trillion cells, there's probably going to be a couple cells that for a variety of reasons are abnormal and are going to do things that could be potentially harmful to the health of the entire body. Well, that happens all the time. What I'm saying is that you and I right now have cells floating through our body that are pre-cancer cells. They're on the verge of becoming cancer. And in a healthy person, our natural killer cells will locate these abnormal pre-cancer cells and kill them before they ever grow out of control to actually create a disease that harms us. In other words, most of us are blessed enough with the ability to live a normal lifespan, 80 years or whatever it may be, and not worry too much about the cancer because our natural killer cells are doing their job on a daily basis to locate these antisocial cells and kill them before they cause us harm. Okay? Thoughts or questions? There's all this activity that's happening to keep us healthy, and we just have no idea. Okay, let's continue. All right. So natural killer cells are the third category of cells I'll mention for you under the second line of defense. Let's go to the defensive proteins. Okay, defensive proteins. Your book does not really give you any pictures of these proteins, so you're going to have to read about them. They are defined for you on page 242, 240, yeah, basically 242, okay? One category of protein is referred to as interferon. Interferon. Okay? Interferon is not referring to a single individual protein, but a whole group or family of proteins. Okay, so this is a group of antiviral defense proteins. a group of antiviral defense proteins, and they do exactly what the phrase says. They are released by cells of your body to defend other cells against virus infection. Okay. Let's see here. Interferon is released by cells that have become virally infected as a warning to neighboring cells that are not infected to protect themselves. Okay, so think of interferon like this. Let's say you come home and you notice that your house has been burglarized. Obviously, that's going to be very upsetting. But as someone who might have a good relationship with his or her neighbors and not knowing exactly when you were burglarized, you might start calling your neighbors and say, hey, Sally, I've been robbed. I don't know when it happened, but it may have happened very recently. So make sure you lock your doors because there could be a robber in the neighborhood and you should protect yourself. That's sort of the idea of interferon. Interferon is released by cells that have already suffered the damage of being infected by a virus. And those cells want to protect other cells so that they don't become infected. Okay? And so what will happen is a couple things here. First off, the interferon that is released by the infected cells will stimulate the uninfected cells to manufacture proteins that inhibit virus replication. Okay, so interferon promotes the manufacture of antiviral proteins in uninfected cells. And in addition to that, the interferon, the interferon that's released, it actually acts as sort of a chemical breadcrumb trail, which will attract it to the defense, which will attract the attention of other defense cells that might be interested in destroying the virus, such as macrophages, natural killer cells that have an interest in destroying the virus or in destroying other cells that are virally infected. Okay, so interferon will act as a chemical attractant to bring other defense cells into the environment to fight the virus. Okay. All right. Okay. Any questions, folks? Okay, let's continue here. All right, so interferon is one category of protein. I have a question for you. Why is it true that a cancer doctor may prescribe interferon therapy for his or her patient? Why is it true that a cancer doctor may prescribe interferon therapy for his or her patient? What do you think, folks? All right, so let's look at each other here for a moment. Why is it true that a cancer doctor may prescribe interferon therapy for his or her patient? Have any thoughts about that? You have interferon, which is an antiviral defense molecule being prescribed to fight cancer. What's the connection? So Quinn, they could warn the other cells to get away so the cancer doesn't spread. Okay, I can accept what you're saying, but what's the connection? Why would I use an antiviral drug to fight cancer? What's the connection between virus and cancer?
It's because your immune system's down and you're more susceptible to viruses. I know that doesn't answer the question as far as fighting the cancer, but it protects you from the viruses that could hurt you because you're more susceptible during that time.
Okay, Catherine, thank you for saying that. I would agree with you. It could be a prophylactic measure to help defend you against viruses that might harm you because your body's already weakened because you have cancer. That's a fair statement. I can accept that. But as you said, it doesn't answer the question. So I like that. It was good thinking. Quinn, what does your comment mean? They affect both, get in human cells.
Yeah, sorry, I did not word that well at all. Like they, both viruses and cancer both get into healthy human cells. Well, healthy human cells. They both kind of corrupt the cell.
So a cancer gets into a healthy human
Oh dear,
cell?
is my internet going out?
Okay, so are you okay with the idea that a cancer is a cell that becomes abnormal? Quinn, is that okay with you? Are you okay with the idea that a cancer cell is a normal cell that suddenly becomes abnormal? Okay, all right. She may be having some trouble with internet, so we'll let that go. Okay, all right, folks, do this. And again, if you can turn your video camera on, I appreciate that. By show of hands, or at least by some kind of indication on the chat window, how many of you, just give me a gut reaction, raise your hand if you appreciate that viruses can cause cancer. Okay, so many of you did not raise your hand, or you might have raised your hand simply because Dr. Allen was raising his hand. Okay, folks, not all cancer is due to the presence of a virus, but at least some forms of cancer are caused by a virus infection. I think you all know this, even though you may not appreciate that you know this. So I will ask this of everybody, but it might mean more to the gals in the class. Gals, have you, or maybe your daughters, gone to the doctor and got a Gardasil vaccination? What's the Gardasil vaccination for?
It's for HPV, the human papillomavirus.
Okay, so Catherine, the vaccine is to protect you against the human papillomavirus. And what does the human papillomavirus cause?
Cancer.
Typically cervical cancer in the gals, right? Can also cause cancer in young men as well, which is why the boys should be getting the vaccine as well. So do you see that you do know, because you got a vaccine, or hopefully you're thinking about getting the vaccine, or you'll get the vaccine for your children, that in fact viruses can cause cancer? Okay, folks, we have known, when I say we, I mean the scientific community has known that viruses are capable of causing cancer for nearly 100 years. Okay. Okay, for nearly 100 years, science has been aware that viruses can create cancer. Okay, so when I have a group of students that don't seem to be aware of it, what's that say about how well we've gotten the word out to everybody that viruses can cause cancer? Okay. Okay, Pete, I appreciate your question, and that could take us down a long path here. I don't know why people are anti-vaxxers either. There's not a lot of good evidence. There's not a lot of good evidence to suggest vaccines are harmful to us. Okay, but we could talk about that after class if you're really motivated to do that. Okay, do you have any questions about interferon? Okay, let's continue. So we'll answer this question in your notes for you. Okay. Some viruses are known to cause cancer. Okay. Such as the human papilloma virus. All right. So if you have cancer and your doctor prescribes interferon therapy, your doctor is playing a hunch that your cancer may be caused by a virus. And so if they treat you with an antiviral drug, it might help defeat your cancer. Okay, let's continue here. Next category of proteins are the complement proteins. Okay, this is another group of defense proteins. They're not necessarily antiviral in nature, but what these proteins do is they complement, hence the name, complement. They complement or assist the immune system. A group of proteins that assist the immune system. All right. And so you do see a picture on figure 13.5 of one of the things that a complement protein can achieve under the right circumstances. Complement protein can bind to a pathogen like a bacterium, cause these little holes or pores to form in the cell wall of the bacterium, which then leads to water coming into the cell overinflating and then popping or bursting like a balloon. And you see photographic evidence. It's not just a cartoon drawing. You see actual electron microscope images of figure 13.5 demonstrating this. Okay, so this is the real deal. So some functions of complement would include the following ideas. When complement protein can bind to certain pathogens, it can lead to the pathogen's destruction. Okay. Can bind to pathogens and destroy the pathogens by creating holes in the pathogen that allow water to enter the cell and burst the cell. Okay? Complement will also attract additional defense cells, particularly the phagocytes, to the particular problem area of the body. So not only does interferon act as a chemical attractant, so does complement protein. Thirdly, You know, one of the scenarios that typically unfolds in the body when your body is having a hard time defending itself against a microorganism is that your defense cells can kind of locate the pathogen. It can kind of see the pathogen, if you will, not in a literal sense because they obviously don't have eyeballs, but they know that the pathogen's there. But when your body's defense cells are not able to physically grab onto the pathogen and destroy it, then that's a problem. So one way that complement will assist the immune system is by first binding the pathogen, and then the defense cells can attach to the complement protein, which are already attached to the pathogen. So in that way, the complement protein can act as sort of a bridge between the defense cell and the pathogen. And by acting as a bridge, the defense cell can physically get at the pathogen and destroy it. Act as a bridge between defense cells and the pathogen. And then the last thing we'll mention here as part of your notes is that complement is one of those substances, one of those categories of molecules that can actually stimulate inflammation. And that's a segue into our next topic, which is the topic of inflammation, which is also part of the second line of body defense. Okay? Folks, do you have any questions about complement protein? Okay, not seeing anything. You folks are quiet today. Let's continue. Okay, we're still in the second line of defense, and our third topic here is going to be that of inflammation. Okay, yes, inflammation. All right, so inflammation is talked about on page 244. You have a nice figure there, figure 13.6. Inflammation is one of those topics that we can all relate to, because I'm quite sure that everybody in this virtual class at some moment of his or her life has experienced inflammation, right? You've experienced a hangnail. You've experienced, a sore pimple. You've experienced a cut that got inflamed. Whatever it might be, we've all experienced inflammation of one variety or another. Okay? So the term inflammation refers to a series of responses, a series of non-specific responses to tissue damage. And what I mean by non-specific is that, if you damage your hand with a knife in the kitchen as you're preparing food, or you damage your hand by falling down outside and getting a wood splinter in your hand, it does not matter what did the damage. It doesn't matter whether you damaged your hand with a knife or with a splinter. The fact of the matter is that the tissue is damaged. And because the tissue is damaged, irregardless of what caused the damage, your body's going to respond with a series of steps. Okay? So let's take a look at these. Here we can list out the symptoms of inflammation. Well, first is redness, right? If you have an inflamed area of your body, such as an ingrown toenail or something like that, it's quite painful, that area is going to be red. It's going to be more red than the surrounding tissue of the body. Okay, so the redness is a localized redness. You're not getting your entire body red. That would be horrible. It's just the area where you have the tissue trauma. Okay, so the redness is caused by dilation of blood vessels in the area of your body that's been damaged. And when the blood vessels dilate, as you know from our previous conversation, you bring more blood into that location. So bringing more blood into that location makes the location redder. This is caused by increased blood flow when blood vessels dilate in response to tissue injury. Okay, what kind of cell did we put in your notes which is responsible for releasing histamine? What kind of cell did we put in your notes which is responsible for releasing histamine? There are actually multiple types of cells that can release histamine, but we only put one into your notes. Do you remember what it was? Okay, Matt, thank you very much. Basophils, that's right. Basophils, another kind of cell that can release histamine, are called mast cells, M-A-S-T, mast cells. These cells of your body will detect damage because the gas environment of the tissue changes when you damage the blood vessel, and that will release the histamine, which will widen the blood vessel, will bring more blood into the problem area. It becomes red. Okay. Another symptom of inflammation is heat. Okay, if you've ever noticed, if you've had an inflamed area of your body, if you touch it with a finger, you'll notice that that area feels warmer, feels hotter than the surrounding tissue. Again, that's also because of the increased blood flow, because as you know, blood is made of cells and plasma. Plasma is made of water. Water has a high heat content because of its hydrogen bonding capability. So if we bring a larger volume of water, a larger volume of plasma into that location is going to feel warmer. Also caused by the increased blood flow. Okay, plasma has a lot of heat energy in it. Okay. We have swelling. Well, obviously we're going to have swelling, right? Because you're bringing more blood flow into that area. So swelling makes sense, but there's a little something here you need to be aware of. Okay. When a tissue swells, it's not just because we're bringing more blood into that location. It's because the blood is leaking out of the vasculature. The blood is leaving the blood vessels and going into the surrounding tissue and accumulating there. So when the blood leaves the vasculature, it's not plasma anymore, it's known as interstitial fluid. So the swelling is caused by the accumulation of blood that's leaking out of the blood vessels. That leaking could be due to the actual physical trauma, which damaged the tissue, but it can also happen because the blood vessels are widening in response to the histamine that the mast cells and basophils are releasing, right? So we could actually widen our blood vessels enough that they get even more leaky than normal, okay? And finally, we also have pain, okay? I mean, we experience pain because the tissue is swelling. When the tissue swells, all that tissue is beginning to stretch, including any nerve fibers that are embedded in that tissue that's swelling and stretching. When that tissue swells, you will generate an action potential, a nerve impulse that gets sent to your brain, and it's interpreted as pain, caused by the generation of nerve impulses along nerve fibers that are embedded in the tissue that is swelling. Okay. Obviously, none of us likes none of us like pain, right? We're a fairly pain averse society. We don't want to have any pain, but pain lets us know that something's wrong, right? There is a benefit to having pain. Pain lets you know that something's wrong, and that if at all possible, you should take corrective action, or at the very least, you should protect that location of your body so you don't cause additional harm. Okay? All right. Folks, inflammation gets a bit of a bad rap. I mean, if you have chronic inflammation that's lasting for a very long time, I'm talking about months and years, yeah, that inflammation process can be part of disease that can cause you harm. But in the short term, hours to a few days, the inflammation is actually meant to be protective for you, because increased blood flow is to bring additional defense cells into the problem site to defend against pathogens, also to bring more nutrients and oxygen into the tissue so that could potentially heal itself. So in the short term, inflammation is protective, okay? But admittedly, long-term inflammation tends to be a problem. Okay, it tends to create more problems than it solves. Okay. Many scientists at this point believe that when a person suffers, say, a heart attack or something, it's likely because in the years preceding the heart attack, in the years before the heart attack, there was a very, very low level, but still very real kind of blood inflammation occurring that was starting to damage the blood vessels, okay? So we really don't want long-term inflammation. That creates new problems for us. But in the short term, we want inflammation to help us heal. Okay, any questions? Okay, folks, I hope you're doing okay. Let's finish the second line of defense by talking about fever. Okay, letter D is fever. Okay. Fever is an elevated body temperature where your entire body, its temperature increases. It's not a localized increase, it's a body-wide increase. Body-wide elevation temperature. Okay. Typically, there are different things that can create a fever. I mean, we most notably think about fever in the context of an infection, right? So if you have the flu virus, or God forbid you have coronavirus, you may run a fever. If you have strep throat caused by a bacterium, you might develop a fever. But we can get fever for other reasons, including cancer, right? Cancer can promote fever formation in the body as well. But at any rate, a fever is simply an elevation in body temperature. And typically what happens is, okay, a typical scenario is when we are infected, okay? Typically what happens is during an infection, the cells of your body send molecules that are called pyrogens into the bloodstream. That blood is then circulated throughout the body by your heart contracting. And some of those pyrogens cross the blood-brain barrier in your central nervous system and the access cells of the hypothalamus. The hypothalamus is your body's master thermostat, okay? So a typical scenario is when we are infected, body cells release pyrogens, which are molecules, into the bloodstream. Which travel to the hypothalamus. which is the body's master thermostat. Okay, so the hypothalamus receives this chemical information from cells of the body that there's an infection, and the hypothalamus triggers responses in the body so that your body holds on to heat energy rather than releasing it. Rather than sweating, you hold on to the heat energy. And by holding on to the heat energy, your temperature goes up. Okay? So, yes, Pete, fever is a natural way to fight off the flu and the virus. That is true, okay? And even though we tend to feel very uncomfortable when we have a fever, I mean, we all do, right? If I have a fever, I don't like going to work. I don't want to go to work. I should not go to work because that's a bad thing, okay? But fever is protective, right? It's going to help you. If you can stand the stress of the fever, you're going to clear the infection more rapidly. So the question becomes this: how is fever protective to us? How is fever protective to us? What's it doing, gang? In what way does having a fever help us fight off an infection? What's actually happening here? Okay, Pete, you say it's using heat to vaporize the bad stuff in the body. Okay, I like some of your thinking. I wouldn't agree with all the wording. You're not literally vaporizing like a laser gun hitting an alien or something. But you have the right idea. Alyssa, the heat helps kill the virus or the bacterium. That's correct, Alyssa. So why would the heat kill the virus or bacterium? Okay, Quinn, I agree with you. We're making it too hot for the bacteria. Why is the excess heat damaging to the bacteria or the virus? What does the presence of the heat do? Think about our conversations in the course for exam 1. What does heat do? If you change, okay, Quinn, how does the change hurt them? How does the change hurt the bacteria? So Alyssa, you say they need a stable environment or they just break down. Why do they break down, Alyssa? What's happening? Okay, let me say something that I hope will trigger some memories here. Okay, what happens to molecules when you change their temperature? Okay, thank you, Nick. Okay, very good. They have a shape change. Okay, all right, so it could be an expansion. Yes, Pete. That's the thing, folks. When you're holding on to more heat energy because you're not releasing it, you're not sweating it out, when your body temperature goes up, the shape of the molecules in your body, including the shape of the molecules making up the bacterium that's making you sick, will change. And if they change their shape, as you know, they change their function, usually in a way so that they don't function as well as they used to. Okay? The excess heat will change the shape of the molecules making up the pathogen, which changes how well the molecules function, and the pathogen dies. Okay? Now there's something to be aware of here. Okay? Think about it. When you have a fever, I don't know about you, but when I have a fever, I just want to lay down. I really don't want to be up doing things. I'm not going to push through my day. It would be it would be dumb to do that, even though we kind of do that sometimes. It's not a good thing, folks. You got a fever, you need to rest. When you have a fever, not only are the pathogens experiencing excess heat and being damaged by it, but the cells making up your own tissues and organs are also trying to survive in that environment of extra heat. And they're also getting damaged. The molecules in your own cells are changing shape, and they're not functioning as efficiently or effectively as they used to, which is why you feel bad. It's why you feel bad when you have a fever, because the very molecules of your cells, of your tissues, of your organs have the wrong shape to do their jobs properly. Okay? Our own cells also experience stress from the fever. And so let's think about this. In perhaps a grotesque way of thinking about it, in some ways, Mother Nature is creating a game of chicken with us, where Mother Nature is taking the gamble that the cells of our own body and our own tissues and organs will be better able to withstand the heat than the pathogen making us sick. If that is the case, the pathogen will die off and we will recover. But if that is not true, if our cells are being damaged more rapidly than the pathogen is being damaged, then our own cells can actually start to die, which can ultimately kill us, which is why very high fevers that are uncontrolled and unregulated can be life-threatening. Okay? So you need to take that very seriously. All right. A point of trivia coming through the chat window. What is the highest recorded body temperature that a person has survived without brain damage? Okay, some good guesses there. According to the resources that I found from Guinness Book of World Records and so forth, it's about 115. Okay, about 115 degrees Fahrenheit. Obviously, folks, you do not want to try to break that record. Okay, even if that record is in error, even if the measurement on the temperature was wrong, you don't want to get anywhere close to that, right? We start hitting that 104 area, you want to take action to bring it down, because that's very serious. Okay, you get a low grade temperature, 101, 101, 102, 103, try to let it ride out. But if you start going above 104, you really need to take action to bring it down, because the temperature should go up. It could go up so rapidly that you become delirious and cannot actually take care of yourself. So if you're not around somebody at that point in time, you could collapse and fall asleep and maybe never wake up. Okay, so be very careful that if you have a high fever, that you're not alone, that you're not by yourself. Okay, folks, do you have any questions at this time? Okay, well, I think we've done a pretty good job today. Here's where we're headed. On Tuesday of next week, I will cover the immune system with you. There's some meaty content in that chapter that has to be talked about. And then we will also cover some highlights of chapter 14 on the respiratory system. Okay? This afternoon, you will get your study guide for your final exam next Thursday. And of course, please remember to take your lab exam today before midnight. Okay? Is there anything else you need help with before we sign off?
I'm sorry, you kind of cut out there. You said the lab exam, and what else about lab today?
I was just commenting, Matt, to please finish your lab exam by midnight. That's all you have to do for the lab.
Okay, so there is no lab lecture.
There is no lab lecture, no lab
Okay.
activity. That is correct. Okay, so when we sign off, folks, please don't come back online in 15 minutes. There'll be nobody online, okay? All right, folks, have a great weekend, and I'll see you on Tuesday. Okay, now.